Welcome to this explainer. Okay, today we are completely skipping those dry theoretical whiteboard diagrams. Instead, we're tapping directly into the live telemetry of an OpenMANET mesh network. Why? Because we're going to deliberately break it and watch the whole thing heal in real time right here on our screens.
Let's face it, right? Literally every network claims to heal itself in their glossy marketing brochures. But what actually happens when we violently unplug a critical piece of that infrastructure? We are taking this into a live, high-stakes hardware experiment to see exactly how network topology reacts when things suddenly go dark. We're not just going to talk about resilience today, we're going to prove it against a real physical fault.
So, first things first, let's establish our grid. We're talking about a MANET. That's a mobile ad hoc network. Just imagine a totally wireless mesh where every single radio node connects directly to its neighbors. There is absolutely zero central router, no fixed infrastructure, and best of all, no single point of failure. The specific project powering our nodes for this experiment is OpenMANET. It uses standard Raspberry Pi hardware paired with Wi-Fi HaLow chips running on those incredibly robust 915 MHz sub-gigahertz bands to build these resilient tactical grids.
Now, running underneath all of that hardware is a really clever protocol called batman-adv. It stands for Better Approach to Mobile Ad Hoc Networking. It's essentially a Layer 2 Ethernet-level mesh routing protocol that creates a virtual BAT0 switch across all the nodes. So, from the perspective of anything plugged into this mesh, the whole multi-hop network just looks like one flat local network. But here is the absolute genius part. batman-adv does not try to memorize the entire network map. Not at all. It purely focuses on finding the single best next hop for every destination. It only needs to know the best next step, not the whole entire path.
Okay, to really understand the telemetry we're about to look at, we need to make a quick distinction between two vital concepts: a neighbor and an originator. A neighbor is a node within direct, one-hop radio contact. Your radio can physically hear them right now. An originator, on the other hand, is any node reachable anywhere in the mesh, even if they are, say, 5 hops away. Distinguishing between those direct neighbors we can hear and the distant originators we eventually want to route towards is the absolute conceptual crux for understanding our live terminal demo.
All right, Section 1, Establishing the Baseline Network.
Looking at our live terminal telemetry here, this is the BAT-CTL originators view, we can definitively see our routing table at work. Check out the columns: originator, last seen, router or next hop, and throughput. If you focus on the row for our ultimate destination, node C, you'll see the router column is clearly listed as node B. What this means is node A has to route through node B to reach node C. Our baseline is established and the grid is completely stable.
So how does this protocol instantly know the best path? To demystify the mechanics here, we've got to talk about Originator Messages, or OGMs. It's basically a constant 3-step flood. Step 1, every single node periodically broadcasts an OGM announcing its existence. Step 2, a neighboring node receives that message and evaluates the throughput of that specific link. And then Step 3, that neighbor rebroadcasts a modified OGM onward to the rest of the mesh. These OGMs are just constantly flooding the network, continuously calculating and recalculating path throughput.
Which brings us to a massive critical number, 1,000. That represents 1,000 milliseconds, or exactly 1 second. This is the default OGM broadcast interval. Knowing this number is super important because it sets our hard reality expectations for exactly how fast our network is going to realize a node has died. This heartbeat ticks every 1,000 milliseconds. That means recovery isn't going to be completely instantaneous. It's bounded by this very specific mathematical rhythm.
Let's move into Section 2, the live node kill.
Okay, power cut initiated, literally, right now. Pulling the plug on node B. I am watching the live telemetry grid and look at the terminal stream. Node B's OGMs have just instantly stopped arriving. You can see the last seen clocked is just ticking up and up. Our mesh has officially lost its middleman right in the middle of an operation.
Let's track this second by second. At 0 seconds, the power physically dies. By about 3 seconds in, those old OGMs from node B finally age out of the system. The protocol recognizes, okay, this router has gone stale. Then by roughly 8 seconds, the surviving nodes are frantically, but mathematically, recomputing the best path based on the most recent surviving OGMs they've received.
And bam, right there is the visual payoff. Look at the routing table again. The next top column for node C just physically updated to our surviving alternate path, node D, in real time. We literally didn't touch a single configuration file. The mesh just autonomously healed itself around the physical fault. The numbers visibly changed right before our eyes. How cool is that?
Now, field tests show an average 8-second recovery out of the box, which frankly is incredibly impressive. But network engineers actually have a dial they can turn. It's a setting called orig interval. This is the ultimate configuration dial for accelerating your mesh recovery speed. By lowering this value from the default 1000 milliseconds down to, say, 500, you can force the mesh to react and heal even faster. And that is highly desirable in fast-moving, high-mobility deployments.
Which leads us to Section 3, why this matters now.
The absolute crucial point here is how this technology is actually applied on the ground in the real world. This exact routing layer seamlessly carries UDP multicast traffic. Now, why does that matter to us? Because transparent UDP multicast forwarding is precisely what carries live ATAK. That's the Android Team Awareness Kit tactical position updates, along with critical disaster response communications. All of this vital traffic rides on the OpenMANET mesh with zero configuration healing. If a radio literally dies in the field, the mesh recalculates, the table updates, and the operational data just keeps flowing without missing a single beat.
I want to leave you with this final thought to really chew on. If this mesh heals this fast and this smoothly just by default, out of the box, what do you think happens when we start tweaking advanced settings, like adjusting the hop penalty to bias the network toward fewer, higher quality hops? Or what happens when we test automatic internet gateway failovers? There is a massive, fascinating ecosystem of advanced protocol tuning beneath the surface here. I highly encourage you to grab some hardware, build your own grid, and honestly, just pull the plug yourself to see what happens.